Blurp. Hokie dokie, yeah, yeah. Hokie dokie, yeah. Yes, sir. It's time for another review session, yeah. Check. Check. All right. Bloop. All right, let's get started. So, welcome to Math 15 or 1025 Quiz 5 review session. Today, we are going to do a ton of problems, and they're all dealing with kind of like introduction to derivatives. So, let's jump into it. Topics, again, intro to derivatives. We're going to be dealing with derivatives of power functions. That's any function of the form x to the a. Exponential functions like a to the x, so any number raised to the x, as well as natural log functions, ln of x. Sine and cosine functions. And then we'll deal a little bit with derivatives and tangent lines. So let's jump right into it. Yeah, let's go ahead and number these. Why not? So number one, let's check it out. So all of these are screenshots of problems that I have individual videos worked out for. I'm going to go through them a little bit faster with more like of a direct explanation on what you need to do for each one. If you need more of a breakdown, obviously look at the videos that you have access to. If you have questions while you're practicing problems, please send them my way. The whole point of these is for me to answer your questions and work them out, each week for you exclusively. So, feel free to take advantage of that. If you have questions, email them to me. Next week is, another exam week, so that might be a really good time to send problems before we go over stuff next week. All right, start with number 1. We're given f of x, and the goal is to identify the graph of f prime. So I'll just state it like this. The slope of f of x will tell us what the y value is of f prime. This is f prime. It's the derivative of f. So the slope of f of x is 0, which means the y value over here should be 0. So the graph with a y value of 0 is blue. So blue is our answer. Let's do one more. The slope of f of x is -1 because we go down 1 and over 1. Got a hair in my tongue. Okay, the slope of f of x is -1, so the y value of f prime should be -1. The color with a y value of -1 is orange. So that's all there is to it. Hope that makes sense. Let's keep going. Number 2. This is testing the idea that anytime you have a derivative of just 1x, the derivative is just 1. So if f is equal to 1x, then f prime is equal to just 1. Same thing goes for any other variable. So if it's f of t equals 1t, then the derivative should just be 1. And it does not matter what x value they're asking about. They're basically saying, like, if you have f of t equals t, then its derivative will just be 1. So then if you were to plug in any x value, for example, e, well, there's nowhere to plug in an x value or a t value, I guess. And so the derivative is always 1 no matter what the t value is. Let's do a couple more like these. So this one is f of p equals e. Keep in mind, e is just a number. So this is testing the idea that if you have a derivative of a number, if you have a function that's just a constant, its derivative will be 0. So f is a constant, f prime is 0, and e is just a constant. So 0 is our derivative of this function. Let's do one more. Here we also have p. We have a variable, but the input variable for this function is r because it's f of r. And so if we do not see an r in this function, then really p is just another constant, and the derivative of any constant is 0. And so you'll notice that if these variables don't match up, then the derivative is just going to be 0. Again, another takeaway is if you don't see the input variable, if you don't see an r in this entire function, then its derivative will always be 0. All right, that was all of what I'm calling number 2. Oh, these were different problems. Oh, well, we'll call that 2. We'll just call all of this 2. Forget it. Okay. Let's call this 3, I guess. Mix it up a little bit. All right, number 3. Pretty much the same idea, a little bit of an extension, though. So if you have a function that's a constant times x, then the derivative will just be that constant. So if we have a constant times x, pi squared times x, then the derivative of that part will just be pi squared. Then, using what we learned a moment ago, if we have a derivative of a constant, well, ln of 5 is just a constant because there's no x attached to it. So ln of 5 is just some number. And so the derivative of any number is 0. So pi squared plus 0, or just pi squared, should be our derivative. All right, we'll keep it going here. Again, same thing. They're asking for the derivative of this function. What did we say a moment ago? We said the input variable is p, and if we do not see an input variable in this whole function, then that means everything here is just a constant, and the derivative of all constants is 0. All right, we'll keep this as a part of 3 here. This is a good one. So we're finding the derivative of all of these. We do see t's in the mix, so the derivative will not just be 0. The derivative of t, the derivative of 1t is just 1. And because it was over 3 originally, it'll stay over 3, or the 1 will stay over 3. And so then the t times ln of 5. Well, that's the same thing as ln of 5 times t, or a number times t. And a moment ago, we just said the derivative of a number times t, or a constant times t, is just that constant. So really, in some ways, these are pretty much like the same derivative rule, where we have a constant times t, and so the derivative will just be each of those constants. So that is 1/3 plus ln of 5. All right, let's keep going. We're going to call this number 4. So this one, I'll sort of just give you the answer because it's really a memorized derivative. So first, like major memorized derivative is this one. So it's 5 to the x. Anytime you have a to the x, the derivative will be a to the x times ln of the a, the base number, right? Let me get this out of the way. All right, so a to the x goes to a to the x times ln of a. All right, number 5. Here is a real demonstration of the power rule in action. So anytime you have x raised to a number exponent, the derivative will be this. The exponent will come out in front. So we'll have 7. We leave the x, and then we subtract 1 from the exponent to get 6. So we have 7x to the 6th. And that's a little bit of power rule for you. That was number 5. This is number 6. Again, x to the 6th. So we take the derivative to get 6x to the 5th. But they're asking not just for the derivative, but f prime at 2.77. And so 6x to the 5th, again, we got by bringing out the 6 and subtracting 1 from the exponent. So we have f prime as 6x to the 5th. And then to find f prime at 2.77, that just means to plug in 2.77 wherever we see x and calculate this here. So let's use Excel. Get a little practice. All right. So 6 times 2.77 raised to the 5th. We get 978 approximately. And that is option A. Hope that makes sense. Let's keep rolling. That was number 6. We're on to number 7. What's the correct derivative formula for ln of x? So this one I will also kind of give to you. Again, it's a memorized one like some of the others. So ln of x has a derivative of 1 over x every single time. Let's keep going. Number 8. That was number 7, right? Yeah. Number 8. For e to the x, the function e to the x, pick the choice that is closest to f prime at 1.31. So the first rule is the memorized derivative of e to the x. Another one to add to your list here of derivatives to memorize. The derivative of e to the x is just e to the x every time. So to find f prime at 1.31 just means to plug in 1.31 in the exponent. And so we will just calculate this real quick. To do e, we do exp in Excel, and then 1.31. Close that off, and we get about 3.7. And that's option B. And we keep it rolling. All right, hope that makes sense. Let's keep going through these. That was number 8. This is number 9. Get a good look at this. They say you may need to use exponent rules as you work through, finally, yada, yada. Okay, so they give us f of x. and they're asking basically what is f prime at 1. So the goal is, can we find f prime first, and then when we plug in 1, what do we get? So let's talk f prime. Using the power rule, we will still, so because we have x to the power of a, the power rule will still be 7/5 comes out in front, and then we want to subtract 1 from the exponent. So 7/5 comes out, we leave the x, and then 7/5 minus 1. You could use you could use a calculator for this and get like decimals. You might be able to convert them to fractions. You could think about it like this. The shortcut, if you need to take away 1 from 7/5, the trick is this. You just take the top number, 7, minus the bottom number, 5, and you divide it by the bottom number, 5. So 7/5 minus 1 is 2/5. 7 minus 5 is 2, and we leave it over 5. So that's our derivative. And then, again, that's just f prime. So they want f prime at 1, so we just plug in 1 in place of x. And so when we plug in 1 for x, we get 1 to the 2/5 there. 1 raised to any exponent is equal to 1. And then 7/5 times 1 is just 7/5. So C is our answer here. Hope that makes sense. Let's do a couple more like this, I believe. I think I have 2 more maybe. Yeah. So same process. Let's talk through a couple sneaky things here. When we have a function that is the square root of something, square root of x, we need to rewrite this function with the help of exponents. And we want to rewrite it in the form of x to the a. So if we have the square root of x, that is equivalent to x to the 1/2. For a square root, there's almost like an invisible 2 right in the root there. So it's like a 2 root, something like that, a square root. And so the original function can be rewritten as x to the 1/2, and once it's in this form, then that allows us to use the power rule to take the derivative. So we bring out the 1/2, we leave the x, and we subtract 1 from 1/2. So using our trick, top number minus bottom number, and we leave it over the bottom number. 1 minus 2 is -1, and we leave it over 2. So -1/2 is our new exponent. So we have our derivative, and then one thing you might see is they might rewrite this as 1/2x to the positive 1/2. So negative exponents can be, those terms can be thrown in the denominator with positive exponents. And then they might go another step to say that, well, if we have x to the 1/2, that's the same thing as square root of x on the bottom. And then if we go another step further, again, that's just f prime. So if we plug in a 2 for x, we're looking for something like this. So 1/2 root 2, and that is option A. So a big shortcut for these. If they're asking us to plug in a 2, we should see an obvious 2 that's in parentheses plugged in. See how we see a 3, a 4, and then like nothing plugged in here? Well, we see a 2 in option A, and so that's what tells us what our answer is. So we could have done that in this last one as well. They asked us to plug in 1, but we don't see a 1 plugged in any of these. We see a 2, a 3, and a 4, right? And then we can use that trick here. Even though the function they give us is a little crazy, I bet you could tell me what the answer is just by thinking about, okay, well, they ask for f prime at 3, so we want to plug in 3 into the final derivative, and we see no 3, a 3, no 3, no 3. So B will eventually be our answer. Let's talk about why. Another function that we have to rewrite in the form of x to the a. So in the last one we saw that when we have a root, we need to rewrite the function so that it's x to the a. Here we have an x term in a denominator that we want to rewrite the original function so that it's in x to the a form. So 1/x to the 11/5 is equivalent to x to the -11/5. So we bring that term out of the denominator and make its exponent negative. That allows us to take its derivative. f prime by bringing out negative 11 fifths, leaving the x, and doing our trick to subtract 1 from the fraction. So negative 11 fifths, we do negative 11 minus 5, and we keep it over 5. So that is negative 16 fifths. We have our derivative. I might rewrite it real quick. Negative 11 over 5x to the positive 16 fifths. Just like that. And then we are plugging in 3, right? So plugging in 3, we just get negative 11 over 5 times 3 to the 16 fifths. And we see that in option B. All right, hope that makes sense. Let's keep rolling. I don't know what number that was. We called all those 9. Those were all the same. Here's number 10. Number 10. They say for f of x equals 8 to the x, pick the choice that is closest to f prime of 1.34. So this was one of our memorized functions from a moment ago, from the start. The derivative of any x, or sorry, a to the x, any number raised to the x, will be that same exact function times natural log of the base number. So natural log of 8. And so that's f prime. So f prime at 1.34 means we just plug in 1.34 in place of x. And let's calculate this in Excel. So 8 to the power of 1.34, and then all of that times ln of 8. And we get 33.74. And rounded, we have 33.7. And that's all there is to it. Hope that makes sense. Let's keep going through it. That was number 10. This is number 11. All right. Below are 4 power functions. Pick the one for which the derivative at 1 equals negative 5/8. So the approach to this one, kind of a shortcut, is rewrite all the functions in the form x to the a, if necessary. And then whatever your a value is should be the answer. So the a value for one of these functions should match the negative 5/8. So let's demonstrate. Let's rewrite all these functions as best we can as x to some power. So this first one, when we have a 6th root, but we have a 5, x to the 5, we basically rewrite that 6th root by like putting the 6 in the denominator of the exponent. So we have x to the 5/6. How about this next one? We have x in the denominator, so bringing x out of the denominator just negates the exponent. So negative 3/2. Now this one's interesting. C, well, if we already have a negative exponent and it's in the denominator, we can bring that term out of the denominator and negate its exponent. And so it was negative 2 and it becomes positive 2. So x to the positive 2 is x to the a in this case. And then this last one, treating it the same as the first one, we have x to the negative 5, and then it's an 8th root, so we divide by 8 the exponent. So again, the a value for one of these should match negative 5/8, and that would just be this last one that we just found, negative 5/8, and that's it. Let's keep going through. Let's do a couple more. Rewriting all of these, we're looking for the one that has an a value of negative 7/10. So this first one, if we rewrite it, bringing the term out of the denominator, we get x to the negative 7/10. So a will be our answer, but let's demonstrate the rest, or rewrite the rest. So at first, on the bottom here, we can rewrite this as x to the 8/6, which is equivalent to 4/3. But we can bring that term out of the denominator as well and call it x to the negative 4/3. All right. And then C, we can rewrite this first as negative 2/5. We have a 5th root, right? So 5 goes in the little denominator of the exponent there. But it's negative, the exponent's negative, and the term is in the denominator. So we can bring that term up to the numerator and make its exponent positive 2/5. And our last one, here's an interesting one again. 1 over x to the negative 1 is equivalent to bringing that x out of the denominator and making its exponent positive. So really just x to the first, or just x. And so we were looking for the one with an a value of -7/10 to match that, and that's option A. All right, here's this last one. We're looking for an a value of 4. Let's demonstrate rewriting all of these real quick. So we have x to the 1 over 4, because the 4th root. Here we have x to the -8, once we pull that x to the 8th out of the denominator. This one's interesting. We have x to the 4/6, which is equivalent to 2/3, but then let's bring that term up to make it -2/3. And then this last one, very interesting. It's equivalent to x to the 8th, but with square roots, we have like an imaginary 2 right there. So x to the 8 over 2, well, 8 over 2 is equivalent to 4. And so that's why this one has D as its answer, because eventually the a value we get from rewriting the function is 4, and that matches the 4 they were looking for. All right, I don't even know what that was. That was number 11. Let's call this number 12. Doing pretty good on time. Let's keep it rolling. G of x is ln of x. Pick the choice that is closest to the y-intercept of the line tangent to g at x equals 1.22. What we need anytime they mention a tangent line is this. We need an x value, we need a y value, and we need a slope value. Okay, so the x value is given to us. The x value is 1.22. The y value we will find by plugging in the x value to the original function. So ln of x, we'll just plug in 1.22. And so let's go ahead and do that, I suppose. Capital ln of 1.22. And we get approximately 0.1989. So y equals 0.1989. And then for the slope, the m value, this is where our new derivatives come into play. So what we do is take the derivative of g, so we find g prime of x, but then we plug in 1.22. So to make this more clear, I guess like the y value was g, the original function, at 1.22, and m is g prime at 1.22. So let's start with this. What's the derivative of g? The derivative of ln of x was one of our memorized ones from earlier. Ln of x has a derivative of 1 over x, and then we will just plug in 1.22 in place of x, and that will give us a slope. So 1 over 1.22 will give us 0.819, maybe, yeah, let's use like 0.82, or 1.9, let's do 0.8197. 8197. All right, so we have x, we have y, and we have our slope now. So let's talk about why we needed those three pieces. So these will be x, y, and slope values we can use for our so-called tangent line. So a tangent line, any line really, has the equation y equals mx plus b. And if we think about it, if we have three of those values, if we have a y, we have an x, and we have an m, we can plug all three of those values in and solve for b. And when we solve for b, we will be solving for our y-intercept, because that's what b represents. So plugging in our y value of 0.1989, our m value of 0.8197, our x value of 1.22 plus b, we should be able to solve for b. So I'm going to multiply 0.8197 by 1.22. So I'll just do this, equals this, which is the 0.8197 times 1.22, and we get, wow, we get 1. That's cool. Yeah, I guess that makes sense because we got that by doing like 1 divided by 1.22, I think. So anyway, we get 1 plus b equals 0.1989, and then we subtract the 1 to get b by itself. So we'll do this minus 1. So we'll do that minus 1, and we get negative 0.8. And b is negative 0.8, and b should be our y-intercept. Here's a good look at that. All right, let's keep going. Number 13. A lot of little derivatives here. Not a lot, but we get into the sine and cosine derivatives now. So sine of p has a derivative of just cosine of p. So sine of x, this is just a memorized derivative, has a derivative of cosine of x. So if f is sine, then f prime is cosine. And almost the opposite, when f of p is cosine of p, then f prime will be negative sine of p. So if f is cosine of x, f prime is negative sine of x. All right, there's our two trig derivatives that are worth memorizing. I'm gonna take a little water break. I'll keep going. That was number 13. Let's call this number 14. Using what we just learned. What did we learn? We learned the derivative of cosine, right? So if they give us f is cosine of r, and they ask us to find f prime at 3.2, we need to find f prime, which is just negative sine of r, and then plug in 3.2 in place of r. Let's see if we can demonstrate this in Excel. Curious if calling this negative sign will work out. I have a feeling it will not. So we get that. Let me make sure it's the same as if we did like negative 1 times sine, because that'd be more accurate just in case. And it still works. Okay, that's reassuring. So negative 1 times sine should give us a positive 0.06. To be exact, 0.05837. All right. Hope that makes sense. Nothing too crazy there. That was number 14. Let's call this number 15. I think we have a bunch of practice ones. Nope, just that one. Sorry, mixing it up. So for this one, little demonstration. We can use what we learned earlier. So they give us h of x, and we need to find h prime at 2. So we're going to take the derivative first. And before we do that, actually, we need to rewrite this function. So h of x can be rewritten as negative 2, and the reason we need to rewrite it is because x is in the denominator. So we bring it up, and we just make its exponent negative. So in rewriting this as basically an x to the a situation, we can now use the power rule to take its derivative. So what we do is bring out the negative 4, and now when there's a number in front of the x term, we're going to multiply the negative 4 by the negative 2, or multiply the negative 2 by the negative 4 that we're bringing out in front. So we make that 8, we leave the x, and then we still subtract 1 from the exponent. Negative 4 minus 1 is negative 5. So now we can just plug in 2 wherever we see x. So h prime of 2 is 8 times 2 to the negative 5. So let's give that a shot here. We'll do 8 times 2 raised to the negative 5. As a result, we get 0.25, which shows up in option A. All right, let's keep rolling. That was number 15. Here's number 16. You know what? This might be a similar example. Yeah, I think these are all. No, I was right. Okay, I have 3 examples of these. I just put them a little more spaced out. Okay, I'm gonna call this just 15 as well then. So same process. If we need to rewrite it, we would, but in this case we do not need to. It's already in that x to the a sort of form. There's no roots and there's no x's in the denominator. So to find h prime, we bring out 2/3, multiply it by the 3. So 3 times 2/3 is just 2. Pretty cool. So you could always plug that into a calculator to get that as well. But 3 times 2/3 is just 2. We leave the x and then we subtract 1 from the 2/3 exponent. This is where we take the top number minus the bottom number and leave it over the bottom number. So 2 minus 3 is -1. Leave it over 3. This is our derivative. So now we just plug in 2. So h prime at 2 is this. 2 times 2 to the 1/3, or -1/3. Let's do that in Excel. 2 times 2 to the, in parentheses, -1/3. We needed parentheses because we had that whole fraction to type in now for the exponent. So we get about 1.587, and we can see that in option A. All right, let's do one more of these same kinds of problems. So again, if we see a root or we see an x term in a denominator, we need to rewrite this function before we take a derivative. So we rewrite it as 2x to the -8/3. Writing it like this allows us to take the derivative. So we bring out -8/3 times the 2. So 2 times -8 is -16. We leave that over 3. We leave the x and we subtract 1 from -8/3. Top number minus bottom number over bottom number. -8 minus 3 is -11. We leave that over 3. And then that's our derivative. So then we just plug in 2 wherever we see x. All right, and that's it. So let's demonstrate that in Excel. -16/3 times 2 raised to the power of, in parentheses, -11/3. Hit enter, and we get -420. Nice. All right. And that's it. All right, that was number, what we're calling 15. Did 3 of those in a row. Call this number 16. I think it's a different kind of problem. So they give us this function, and they are asking for the derivative at a bunch of different values, and they're just like hoping that one of those is correct, right? So the first step is to find the derivative. So the derivative of u of s would be u prime of s, and so let's talk about how we can handle this. 5 to the s we can take the derivative of, and any coefficient, any -3 that's out in front, can just kind of stay there while we take the derivative of the important piece next to it. So 5 to the s times ln of 5. This goes back to the exponential rule earlier, where we have a number to the s or a number to the x. Its derivative is always that same thing times the ln of the base number. So we have this derivative right here. So what we can do is play around with Excel and try out different numbers here. I'm just going to do 3/2. Oh no, I messed up. I'll never see the end of that one. Okay, let me start down here. We'll do equals 3/2. And then we'll do 5 and 4 and equals 9/2. And then if we're smart here, what we can do is just input this function, the derivative function, once, and then we can drag it down, and then we can see which one of these 4 values actually matches. kind of finesse it like this. So equals -3 times 5 to the s. So we'll click on that cell, times ln of 5. So we input the derivative, and where we saw s, we clicked on the s value. All right, so now what we're going to do is drag this down, and what it does is actually calculate all the derivative values at each of these x values or s values. Yeah. So when we scan through these values on the right, which one of them matches which one of these? So -53, -120, no. -15, -33, no. -3017, -3017, yep. And then the last one, -67, -15, nope. So C must be our answer. So that was kind of a fun, creative way to go about it in Excel. All right. Number 17. Here they say the surface area is proportional to the square of its radius. You don't need to think about that. They're just giving us the surface area equation. And they say, what is the best estimate for S prime when R is 156? So the idea is just to calculate whatever S prime is by taking its derivative, and then we'll just plug in 156 in place of R. So when we look at this here, we know how to take the derivative of R squared. So we're just going to do that. And 4 pi is just a constant or a coefficient, so it's just going to stay out in front unbothered. So it's going to be 4 pi, and then we take the derivative of R squared to get 2R, because we brought out the 2, leave the R, and now R is to the first power, or basically just like that. So we have 4 pi times 2R. We can multiply the 4 and the 2 to get 8 pi, or I guess 4 and the 2 to get 8, and then we leave it by the pi times the R. So S prime is just 8 pi R. So that's our S prime, so we just plug in 156 in place of R. All right. So using Excel, we'll do equals 8 times, I wonder if pi works. I don't know how that works. Yeah, there it is. Just pi gives you pi. That's pretty cool. Times 156. Oh, that did not work. What the hell? All right, I think you got to do like that, maybe. Okay, yeah, I'll take that. Yeah, I think that's right. You just got to do parentheses like that. Okay, okay. Yeah, so we get about, what, 3920? 3920. We see that more or less here or here, B or C. And then because they're asking about surface area, that's units squared. So C is our best answer. Whereas when you see an example with volume, like we're about to work out, our answer must have the cubed units. So given this volume equation, we're going to take its derivative. So again, with everything that's not the R cubed, the R value there, we're going to leave the 4 pi over 3 kind of like out on its own, and then just take the derivative of the R cubed. R cubed has a derivative of 3R squared. We bring out the 3, leave the R, and subtract 1 from the 3 to get 2. So then we have this, and multiplying these two together, we can actually cancel the 3's out, and all we're left with is that V prime is equal to 4 pi R squared. Then they want to know what's V prime when the radius is 117. So we're going to plug in 117 in place of R. So let's give that a go. Equals 4 times pi times 117 to the second. Hit enter and we get about 172,000. And we know it should have the units cubed, so about 170,000 looks pretty solid. So that was a glimpse at both of those here. We had the surface area, we had the volume example. That is what we called 17. So here's number 18. I told you we're doing a lot of problems today. A lot of good stuff. So this one is a doozy sometimes. They say below are 4 power functions. Pick the one for which the derivative at x equals 2 is approximately negative 0.729. So the idea, honestly, is we have to rewrite these functions if necessary. A lot of these we do not need to rewrite except for option D here. We rewrite it with negative exponents. And once we've rewritten all these functions, we need to take the derivative of all these functions and then plug in 2 to all these derivatives and then see which one equals negative 0.729. So let's give it a shot. Taking the derivatives first. We bring out 3/8 times 3. We get negative 9/8. We leave the x, subtract 1 from the exponent by doing top number 3 minus bottom number 8. 3 minus 8 is negative 5, and we leave that over 8. Let's find all our derivatives first. So the second one, we bring out the negative 3 over 32, or basically we bring out the 3 over 32 and we multiply it by that negative that's out in front. So it just becomes negative 3 over 32. We leave the x, and then 3 minus 32 is negative 29, and we leave that over 32. Keep it going here. I'll write this one way out here so we have space. 3 halves will come out in front. Leave the x, and then 3 halves minus 1 is 1 half. So 3 minus 2 is 1. Leave it over 2. Then this last one. Negative 3/16 comes out in front, multiplies by the 3. So negative 9 over 16. We leave the x. Negative 3 minus 16 is negative 19. Leave it over 16. So we have all 4 of our derivatives here. Now we're just going to plug in 2 to each of these. And so let's see if we can use Excel to the best of our abilities here. I'm just going to plug a 2 in right here. Whoops. So I'm plug 2 in right here. And I'm just going to input each of these derivatives in order and then click on 2 wherever we see x, I guess. So starting with the first one, we'll do negative 9 over 8 times, I guess I could just do 2, it doesn't really matter, raised to the power of negative 5/8, so negative 5 over 8 in parentheses. Alright, so I mean right away we get negative 0.729, so our answer should be A right away. Yeah, I'll probably just leave it at that. There's no need to go into it any further, but you know, you would plug in 2 to each of these other ones and see which one would equal that if A were not already our answer. So A is our answer there. Let's keep going. That was 18. This is number 19. This might be the last one I have for you, actually. All right, not bad. We went through a lot of problems in about 45 minutes. Let's talk about this one. Actually, we've already seen this one, so I'll just kind of redo it, but it's just, you know, they have a different function is all. We're finding the y-intercept of the tangent line at a certain x value. For the tangent lines, I mentioned we wanted an x value, which they give us. We wanted a y value, which we will get by plugging this x value into the function. So sine of negative 0.55. And then we want a slope value, which we will get by plugging in the x value into the derivative of the function given. The derivative of the function given is cosine of x. And so we will plug in the x value of negative 0.55. So we have our x. Let's calculate y and m. So sine and cosine. So sine of negative 0.55. And we'll go ahead and do cosine. Cosine of negative 0.55. All right, looks good. So our y value is negative 0.523. Our cosine value or our slope value is 0.853. 3, I guess. So we have everything we need, x, y, and m. So we will plug them into y equals mx plus b. And our goal is to solve for b, which is our y-intercept. So plugging in y, x, and m, we will get negative 0.523 equals the m value, 0.853, times x, which is negative 0.55, plus b. And then, yeah, so let's multiply these two and then subtract it from the left side. So we have this value here, and then we'll multiply it by negative 0.55. And we get negative 0.469 plus b, and then we'll just add 0.469 to the left side, to both sides, I guess. So we'll do that number, yeah. So we'll do negative 0.523 right here, plus 0.469. We get about negative 0.554 maybe. Let's see what we have for options here. So this is kind of one of those annoying ones, but to pick the choice that is closest to the y-intercept, I guess if we rounded this up to the nearest tenth, would be negative 0.1, because that 5 would round that 0 up to a 1, and that must be our closest bet there. Not the most ideal answer, but definitely the closest of those options. All right. Hope that makes sense. I'll just scroll through all the problems we've done today. And if you have questions, as always, please let me know. I'm just going to scroll through each one and call it a day. Covered a lot of stuff. Almost everything I probably have videos for, like in this quiz, really. Covered all of our topics. Let's get going. Derivative of x is 1, or derivative of t is 1. The derivative of a constant is 0. The derivative of a constant times x is just that constant. If you don't see the variable in the function, the derivative will just be 0. And again, the derivative of any constant times the variable is just the constant. Any exponential function with a number raised to the x is that number raised to the x times ln of the base number. Any power function x raised to some number, we bring out the power, leave the x, and subtract the power by 1. Ln of x has a derivative of 1 over x. E to the x has a derivative of e to the x. Anytime you see a root, you'll want to rewrite that function as x to, in this case, if it is a square root, x to the 1/2. If it's a cube root, x to the 1/3. If it's a fourth root, x to the 1/4, and so on. You always rewrite it before you take a derivative. If you see any x terms in the denominator, again, you'll want to rewrite that function first before taking the derivative. This one, there was kind of a shortcut. Just rewrite each of them, and then whatever your a value is shows you what your answer is. Derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. Thanks for hanging out with me, whoever the 1 or 2 people watching these things is. Alright. Blurp. Thanks for checking this out. I think I'm going to call it here. Let's wrap this baby up. Alright. Thanks so much. I'll see you next week when we review for exam 2 on quizzes 4 and 5. Alright.